Okay, we're going to get started on our next topic. It's pretty small, this one, especially this year, because we're not going to be doing carbon nanomaterials. So to begin with, we're going to focus on what this next little unit's about. And it's all about the whole rest of this area of study is all about one magical element. It's all about this guy here. It's all about carbon. So what I'd like you to do is I'd actually like you to stop this video and go back, if you haven't already watched it, and watch the little video that introduces you to carbon. It's just a little old school YouTube clip that talks about it. So our first part of carbon chemistry that we're going to discuss are covalent network lattices. So here is our bullet points here. We're going to be definitely doing the first one, which is the structure and bonding of diamond and graphite, and explaining their properties and what we use them for. The second one here about nanomaterials, including graphenes and fullerenes, they're in this PowerPoint, but you don't need to know them. So if you would like to read up on them, you can do that. And who knows, I might end up making a video on them just for interest's sake or for next year as well. So we're going to start off on the book that starts with a big 7 in a blue box up the top that says Networks and Nanomaterials. And underneath it, it says Covalent Network Lattices. And it starts to talk about carbon. So it says carbon is present in all forms of life. It forms simple, small molecular substances like carbon dioxide and methane, so CO2 and CH4. But also larger molecules like C60, H122. Okay, so carbon can make very hard substances and very soft substances. It can be an electrical conductor as well as an insulator. But how can it be all of these things? That one element can make up all of these things. So carbon, then I'm just going to keep reading down these notes so that we finish them on this page, and then we'll have a discussion. So carbon can bond with itself in many different forms. These structurally different forms are called allotropes. So that word here is an allotrope. So they're made up of the same molecule, yeah, or the same atoms, but they have different structures and different ways about them. So therefore we call them allotropes. The different allotropes of carbon are the reason why carbon has so many different properties. 2 allotropes that we're going to talk about of carbon are diamond and graphite. And it says the structure of diamond is described as a network lattice. Yes, so network lattice. And the structure of graphite is described as a layer lattice. And we'll talk about each one of those. And this first video is going to talk about diamond, and the second video is going to talk about graphite. So these giant covalent lattices are solids at room temperature. Yeah, because you can see here are their melting temperatures, and they're very high, so therefore they're going to be solids at room temp. And require exceptionally high temperatures to melt. Okay, so they're going to be solids at room temperature. So let's get started on our next page, which is all about covalent network lattices. So we're going to start talking about these pretty things on the right here. We're going to talk about diamonds. So diamonds are the hardest, this is your gap, yeah? The hardest naturally occurring substances known. And we use industrial diamonds, so they're not just for pretty jewelry, but we use them in machinery for drilling, cutting and polishing. We do use them in jewelry, and also they use them in dentist drills. So next time you go to the dentist, think about them drilling out your teeth and all of those horrible things, but you've actually got diamonds in your mouth at that time. How cool is that? So one of the strongest types of bonding between particles in a solid is that of a 3D covalent network lattice. So this is the strongest bonding ever. Have a look at it. It looks strong. It looks like all of those angles are building it up to make something that's very strong. So 3 covalent bonds exist in all of these directions. I'm going to have to change my color there. Yeah. So they exist in all of these 4 directions. So if you think about it 3-dimensionally, that's 1 up and then 3 kind of out down the bottom like that. So covalent bonds extend in all directions in the crystal structure. Diamond is one such substance that has a covalent network lattice. diamond is comprised of carbon atoms. So here is a carbon atom, and it is bonded covalently to how many? So I'm going to pick this guy in the middle. I'm just going to get rid of these pen markings so we can have a look. Yeah. So each one of these carbon atoms is bonded to how many? 1, 2, 3, 4. Yeah. And if you picked any one that was in the middle of that lattice, you would see that every single one of them is bonded to 4 other atoms. Now, being bonded to 4 other atoms in a big lattice, that's going to make you really, really strong and really, really hard to break. So hence, it's made up entirely of intramolecular covalent bonds, which is why it's very, very strong. All right. Last little bit for this video is to talk about the properties of diamonds and the properties of covalent network lattices. First off, they're very hard. So diamond has strong covalent bonds throughout the lattice, with all atoms being held in fixed positions, okay? Because of these fixed positions. I don't know why that's making noise at me in the moment, but that's okay. It's also a non-conductor of electricity. If we go back here, can you see any free moving charged particles? No. So what do we know? It's the same concept coming back again. No, there's no free moving particles at all, so therefore we won't conduct. But there's also no free moving charged particles. So therefore we're not going to conduct electricity. The next one is it's actually a high conductor of heat. Now, being stuck in this lattice means that if you give these atoms energy, they're just going to vibrate really, really quickly. Yeah, because they don't want to move out of positions. They're just going really, really quickly. And imagine if you're really moving really quickly. Heat can get passed through that really, really effectively. So that third dot point says that they are a high conductor of heat because the atoms are held together so strongly that they vibrate extremely quickly, therefore heat can be passed through effectively. The next one is talking about the high melting points. There are so many covalent bonds in here. We know that covalent bonds are super strong. In order to break apart those covalent bonds, what are we going to need? A lot of heat. So high melting points, diamond has strong covalent bonds throughout the lattice, hence a lot of energy is required. Now, diamond's actually interesting. It doesn't melt. It would go straight to a gas if you got it hot enough, which is how hot? This hot, yeah, 3,550 degrees or more. You can see that there's no boiling temperature here, that we've actually been able to turn it into a gas. And so what happens is that they just straight away kind of like evaporate, which is pretty crazy to think that you could get a diamond to that temperature and it would just evaporate. It's not going to happen very easily. They're chemically inert again. If we've got no particles that are moving around, why would they want to react with anything? They're so happy just sharing their electrons with their 4 other carbon atoms. Now, these are very, very directional bonds. So due to the directional bonds in this lattice, now, if you tried to move them slightly off, what you would get is you would get a shatter. Yeah, so straight away you're going to get a brittle substance. So again, they're very hard, so it's quite hard to cause them to break apart. But if you do strike them right, you can get them to break apart. So there are a couple of other covalent network lattices. You don't need to know about them, but silicon carbide, and silicon dioxide. Silicon dioxide is what you find in sand. Yeah, so it's interesting to think that sand is actually a covalent network lattice. And so that's the end of the first video on covalent network lattices, and there's one more on covalent layer lattices.